All right, welcome to module number 4, the final module in the 4.6 Related Rates series. Hope you've been having fun. So for this final module, we're going to be dealing with trigonometry problems, which, again, it sometimes gets confused for Pythagorean Theorem, but what sets these problems apart is that there will always be an angle that you're dealing with. So if you ever see a theta, or if they mention something with its radians changing, you can pretty much be certain it's going to be a trigonometry question. So in this type of problem here, if you're dealing with an angle of elevation, so if you're looking at an object that's in the air and it starts to rise or fall, that changes the angle you're looking at. So that would be a common situation. Another kind of problem might just be a right triangle where they tell you that one of the angles is changing. Now keep in mind, if an angle changes, so do the sides. So trigonometry is really the study of how those sides and angles are related, and as these things start to move, here are the essential skills you're going to want to know about going into these problems. So, to begin, you really want to make sure that you understand how all right triangles are labeled and understood. So if you take a look at this triangle here, I'm going to do one thing, which is just highlight the main angle that we're dealing with. So when you look at this problem here, you'll notice that that theta is put right here on that angle. Now the theta is never going to be on the right angle, it's always in one of these two places, either here or potentially in the other angle. So what I'm going to do now is ask you to actually fill out the 3 side names, if you remember what they're called, and I'm going to pause here and see if you guys remember from trigonometry what you call each of these 3 sides. Okay, so go ahead and I'm going to pause the video now and try filling in those 3 sides. I'm still here. This is kind of creepy. Okay, welcome back. So, hopefully when you guys labeled these 3 sides, here are the names that you guys should have written down. So, the easiest one to remember is the hypotenuse, because that is our longest side. And if you're ever not sure where your hypotenuse is, all you have to do is actually just look at that right angle and look directly opposite of it. And if you do that, you'll see that you're dealing with the hypotenuse. Okay? Now the other 2 sides are really important to realize these distinctions. If you look at where this angle is, where it's opening up to, when you look across the triangle at this side here, that's what we reserve for the side called opposite. And if you look at this side here, the one that's next to the angle in question, there's actually 2 sides that are next to it. One is the hypotenuse, one is this side here. That is called the adjacent side. So just make sure anytime you're dealing with a right triangle, whether you create it or it's given to you, that you're always identifying which side is the hypotenuse, which side is the adjacent, and which side is the opposite. So, knowing these 3 sides then, here's the main task. In any trigonometry question that involves related rates, you're usually dealing with 2 out of the 3 sides. So the first decision you have to make is which trig ratio should you use if you're dealing with, for example, opposite and hypotenuse. Or what if you were dealing with opposite and adjacent? Well, the way you make that determination is by knowing your 3 trig ratios. So you might recognize this acronym, SOHCAHTOA, because in geometry, when you first learned about right triangle trigonometry, you needed a way to memorize these 3 ratios. The first one being called sine, the second one being called cosine, and the third being tangent. Now at this point in calculus, you've seen these 3 functions time and time again. You know that they're trig functions that have waves for graphs, but remember where they came from. They came from right triangles, and they represent the ratio between 2 of the sides. So the way you learn how to do this, and really the easiest thing to remember, is that all the O's in the word SOHCAHTOA represent the opposite side. So I'll fill those in. All the A's stand for the adjacent side, and the H, of course, stands for the hypotenuse. Now, when you first learn SOHCAHTOA, the most important thing to learn is how it's spelled. When you say so, you have to know that represents SOH, because the sine ratio is simply opposite over hypotenuse. When you learned how to spell SOHCAHTOA, the ka has to be spelled CAH, because that represents the adjacent over the hypotenuse ratio. And finally, TOA Pretty hard to mess this one up, but TOA is spelled T-O-A, and that represents the opposite side over the adjacent side. So here you have three trig ratios: sine, cosine, and tangent. So in this case here, you've got three trig ratios, and you really should have these memorized, or if not, make sure you remember SOHCAHTOA, and that'll have all the information you need for what these ratios are. Now, in geometry, you learned these three trig ratios, but later on you learned that each of these three trig ratios has a reciprocal as well, and we've dealt with this stuff a lot this year. If you remember the reciprocal of sine, if you think about which trig function has a third letter that starts with S, that's not a good way to remember it, but the reciprocal of sine, hopefully you guys remember, is cosecant. The reciprocal of cosine is secant, and then the easy one to remember is the reciprocal of tangent, we call cotangent. Now, for some reason, everybody always loves SOHCAHTOA. I don't know, it sounds like some tribal chief name, SOHCAHTOA. But lesser known is the cousin of SOHCAHTOA, which sounds like something else entirely, but this one might help you guys remember what cosecant, secant, and cotangent's ratios are. If you think about how each of these reciprocal functions is merely the reciprocal of these three fractions, look at what we end up creating when you try to learn these other three functions. Cosecant, for example, will be hypotenuse over the opposite side. Secant will be the hypotenuse over the adjacent, and then cotangent will be the adjacent over the opposite. Now, I'm totally kidding. This is not something that ever gets taught. In fact, I'm pretty certain no one else out there ever has said these words. But if you want to try to think of how you could remember these three reciprocal functions, I suppose you could read this acronym. Choshakao. And if you remember Choshakao, then really the three trig functions that you knew from SOHCAHTOA all just get flipped upside down. So should you memorize this? Doubtful, but hopefully this helps you remember that the three reciprocal trig functions all have the reciprocals of the originals. So just real quick, our hypotenuse again in H is here and here. So now the hypotenuse would be on top. For a cosecant, opposite would be your denominator. Same with cotangent. And the adjacent sides would be the denominator for secant, but then the numerator for cotangent. Okay, so anyways, you got three more trig functions, and they're reciprocals if you want them. And I've drawn a pair of snowmen. Yay! And they're going to hold hands. Aw, adorable. So, ladies and gents, you've got your trig ratios, SOHCAHTOA and Choshakao, and you know what hypotenuse, opposite, and adjacent look like on a triangle. So, let's move on to our examples using all this information. Okay, for our first example of trig questions, we're going to deal with a problem where we know the angle of elevation. Now, compared to not knowing it, this is a much easier type of problem where really we just got to make sure that we know what angle we're dealing with and what trig function to use. So it tells us about a hot air balloon rising straight up from a field, and it's being tracked by this device called an inclinometer, which pretty much just tells you what angle you're looking at something in the sky. Now, as the balloon rises, it tells us that there's a moment when the angle of elevation is exactly pi over 4 radians. So there's that key information that tells us the angle we're dealing with. Now, since the angle is increasing at a certain rate, they're asking us how fast is the balloon actually rising from the ground. Okay, let's get a diagram drawn for this thing before we get any further. So here is my level field, and we need to draw a balloon rising. So don't draw it on the ground, draw it somewhere in the air. And I guess, yeah, here's my drawing of my balloon. There's the place where people stand, and here is the balloon and the strings. That looks like a light bulb. Okay, so let me just... Okay, that's not helping. Okay, and let's just put some nice color to this thing, and There we go. What a lovely hot air balloon. Okay, that's the worst thing I've ever seen. All right, ladies and gentlemen, there's the hot air balloon rising at that moment. I hope you enjoyed the art video there. Okay, so what's actually happening in this problem that's changing? So we're going to get a distance here for where the inclinometer is and where the liftoff point is. So let's just draw a line going straight down, and that's going to represent the liftoff point, which is perpendicular to the ground, and the inclinometer, which is here in this corner, that's going to be tracking the hot air balloon. So I'm going to draw a line going that way, and voila, there's a right triangle diagram. Okay. Now, when you read through the question, here are the things that are changing. If you're standing right here watching this hot air balloon travel upward, that means the angle that of elevation that we have is technically this angle right there. And so label that with a theta. Now, the other information is that the inclinometer is 500 feet from the liftoff point, which is there. So I'm going to label this constant with a 500 feet because that amount will not change. Now, the last thing to realize is we know that the balloon is rising up in the air, so this side here needs a variable name. So let's go ahead and call that h. So according to this diagram that we have here, what I'd like to see if you can do correctly now that I've labeled the variables and put down the constants is I want you to read through the problem and try to figure out what information goes with which variable. Now remember, we have normal variables and we have derivative variables, rate variables. So pause the video and go through and see if you can highlight any important information, and then check back in with me once you've done that to see if you correctly identified whatever important information would be. Okay. Also identify what is the question asking us to solve for. Good luck. Okay, and welcome back. So if you went through this question, hopefully you caught these different pieces of info. They tell us, in a very, very important piece of information, right there, that at the moment the angle of elevation is pi over 4 radians. Now, what is that? Well, we know that theta represents our angle, but is this telling us the angle or the rate at which it's changing? Now, read it again. It says angle of elevation is pi over 4 radians. So that means we can go with d theta, that means we can go with theta equals pi over 4 radians. They tell us specifically that that is what the angle is. Now, read how this part sounds different. It tells us that the angle is increasing, and there's that word, at a rate of 0.14 radians per minute. So based on the units or based on what the information says, hopefully you recognize that is telling us d theta dt is 0.14 radians per minute. So there's our rate variable. Now, the 500 feet was a constant that we don't need to highlight, but the last and most important thing to realize is they do tell us what we're going to search for, or what we need to solve for, which is how fast is the balloon rising at that moment. Notice they don't say how high is the balloon. They say how fast is it rising. So what we need to solve for would be dh dt, and that is what we're going to try to solve for. Okay? So hopefully that's what you picked up on as well as you read through the question. And now comes the most important step in problems like this. If you take a look at the diagram we have, this right triangle. Here's our angle. This is a side that we know is 500, and this is a side right here that we know is important for our height. Notice how this side here was never even discussed, which means that side there is not relevant to this problem. So my question to you is this. Which trig ratio or ratios could be used if you're referencing, or the angle that we're dealing with is here, and you're dealing with this side and this side? First of all, what would you name those sides? And then look at your SOHCAHTOA or CHOSHAKOW and answer that. Which trig function do you think you would use in this problem? I'll give you a second to figure that out while you pause the video. See if you can determine what trig function we'll use. Okay, did you get tangent or cotangent? Hope you did. First off, this side here is technically considered the opposite side, and this side here is considered the adjacent side, and I don't know why I have my highlighter on. So, the only trig functions that don't use hypotenuse, that would either be tangent or cotangent. So how do you decide which one you want to use? Well, let me ask you something. In the tangent ratio, SOHCAHTOA, TOA, we would need to write the opposite over the adjacent. That would be h over 500. In the cotangent case, we need CHOSHA a over o, so the adjacent, which is 500, over the o, which is, or the opposite, which would be h. So which one of these equations is actually easier to use? Well, they both look pretty similar to me, but let me ask which derivative would be the easier derivative to take? Well, you need to know your trig derivatives, but I actually want you to take a look very specifically at the right sides of the equation. Now, let's take a closer look at this. If we wanted to know which trig function had an easier derivative, let me show you both. For the first one, derivative of tangent, we know to be secant squared theta, but remember, you have to multiply that by d theta dt. Now, if that seemed complicated to you, that's just knowing your trig derivatives still from back in chapter 3. So what about the right side? If I ask you to take the derivative of h over 500, please don't use quotient rule here. This is a problem where really you should understand that h over 500 is really just 1 over 500 times h. So that derivative is actually very easy to take. It's simply 1 over 500, and then derivative of h is dh dt. Okay, so there's the derivative if we want to use tangent. Now take a look at what happens. Take a look at what happens if we took the derivative of cotangent. So you get the derivative of cotangent is a lot like tangent, except it's negative, and you get cosecant squared theta times d theta dt. Now that's actually not any more difficult than what we did before, so let's take a look at what happens on the right side. How do you take the derivative of 500 over h? Again, instead of using quotient rule here, think about how that h is in the denominator, and if you remember the derivative of 1 over x, this is very similar. You'll get negative 500 over h squared, and then don't forget to multiply by dh dt. Now, when you take a look at this derivative compared to this derivative, which one's easier? Well, you might say they're both easy or both difficult. You might not see the difference with which one's more complicated. But look at how many variables the two equations have. Do you notice that the one underneath has an h squared here? And in this case, well, there's no h whatsoever. So why use this equation when there's more things to worry about when you can really use this one? These are the kinds of decisions that you have to make when dealing with trigonometry-related rate problem, and to realize that this equation really isn't worth it because it only gives us more work to do. So when we were trying to figure out which one of our trig ratios to use, maybe you pick tangent just because that one seemed like the most obvious one, but you really want to go through and think through which one would be the easier derivative to take. Okay? Since this quantity is always going to be the reciprocal of that quantity, just figure out which one's easier to deal with. Okay? So now that we've finally made our choice here, sorry for taking so long to explain that, now let's get to work and do what we know to do. Let's plug in as much information as we can here. So we get secant squared of theta, which I believe the problem tells us, times d theta dt is equal to 1 over 500 dh dt. So let's take a look at the information we knew from before and make sure we get all this information in correctly. So we are going to solve for dh dt, which is nice because that means we don't need to plug anything into that part of the equation. The radian, they tell us, the angle, is pi over 4. And the rate at which the radians are changing, d theta dt, well, that would be 0.14, which again, all that information was given pretty early on in the question. So let's solve this. Since we're dealing with a trig problem, just thought I would make sure you guys know exactly how I find all this information. So, first off, if we have secant squared of pi over 4, my question is, how do we calculate that value? Well, on a unit circle, we know pi over 4 to be that location right there, the wonderful place where root 2 over 2 and root 2 over 2 are the x and y values. So what is secant? Well, secant is the reciprocal of cosine. And what's cosine? Well, not that it matters in this case, but it would be the x value. So what I'd like you to do is think about how secant is really 2 over root 2, but since it's secant squared, I know that I have to take that quantity and square it. Why am I making such a big deal of that? Well, it's because that's a skill that just so often people forget or try to shortchange when really you want to go through carefully and make sure you get that correct. Okay? So now what I want to do is finish off the rest of this problem by plugging in the other numbers. So we have still our 0.14 equals 1 over 500 dh dt. Okay, so in purple there, if you were to square the quantity 2 over root 2, you get 4 over 2, which is in fact just 2, times 0.14 equals 1 over 500 dh dt. Now continuing onward, calculator would be nice here, but I don't think this question has a calculator icon next to it, so let's just keep going by hand. This would be 0.28 equals 1 over 500 dh dt. And so now we do have to multiply both sides by 500. So if you multiply 0.28 by 5, I think you end up getting 1.4. And then if you multiply that by 100, then you can move the decimal place over. So I believe for this answer we should get dh dt is equal to 140, I believe. And in this case, this is how fast the balloon is rising. So this will be in feet per minute. So ladies and gents, there's our answer to this first example. Hope it made sense. Hope you enjoyed it. Let's take a look at the next problem. Okay, for example B, first off, it's a calculator active question, which will make our lives a lot easier. However, look at the title of this problem. It is an unknown angle of elevation. So this question actually reads very similarly to the previous one. There's something on the ground measuring how high a hot air balloon is rising into the sky. Now, when you read the problem this time, notice there's no mention of what the angle ever is. This is a huge issue for people because people don't know what to plug in for theta in this situation. So first off, let's get a diagram drawn just like before, and you'll notice a lot of the same ideas are coming into play. All right, so first off, here's our field, and just like before, my ability to draw a balloon is probably the hardest thing about this entire question. All right, there's my basket, and hey, that one looked kind of better. Okay, well, that will do. That's not bad. Yeah, okay, I've seen worse. So, ladies and gents, there's my balloon, and again, it's rising off the ground. Whoa, that was horrible. It's rising off the ground here, straight down to a perpendicular, and there's an object, a camera in this case, tracking this thing's movement, okay? Now, if you again notice that there's going to be an angle of elevation, since that camera is tilted upwards, so there's our theta. The ground is 200 meters away, so there's our 200 meters, and once again, we're dealing with how high the balloon is off the ground, okay? Now, once again, I'm going to ask you to pause the video and read through the problem, identify any variables that are needed, and pinpoint what question the problem is asking us to solve for this time. It is different, okay? So pause now and read through, highlight, and write down any variables. Tick-tock, tick-tock. I said pause the video. No, seriously, pause. Wait, this doesn't make sense. Okay, so you're back. All right, here's what you should have noticed about each piece of information. 200 meters, that is a constant. However, they tell us the balloon is rising at a constant rate of 10 meters per second. I just realized this word constant can be a little bit tricky. So the balloon rising into the sky at a constant, balloon rising in the sky, let me try that again, at a constant rate of 10 meters per second. I know the word says constant, but that's not a constant. It just means that while the balloon is rising in the air, we need to talk about its rate. So that would be dh dt equals 10 meters per second. Okay? Now, other than that, they tell us once the balloon is 150 meters in the air. So I know that the balloon is rising, but it says when the balloon is 150 meters in the air. Now this means that at some point we know the height of the balloon is going to be 150 meters. This changes, so don't label this as 150. Keep it as an h. But just realize there will be a moment when we need to know that the height of the balloon is 150 meters. Now, what did the question ask us for this time? Well, hopefully you noticed that when they ask you how fast, they are specifically wondering how fast the angle of elevation is changing. So what does that mean here? It means that we need to solve for d theta dt. Now, again, an issue with this problem that some people worry about, they never tell us what the angle is, and they never ask for it either. We don't need to know what theta is in this problem. A little bizarre, but again, watch what we do here. In order to figure out which trig function will be used, again, this is the same scenario, so since we're dealing with the adjacent side and the opposite side, I'm going to go ahead and use tangent of theta equals opposite over adjacent, so h over 200. I can tell you right now, because it's the same setup, this is the best way to do it, not using, not using cotangent, because, again, the less stuff that we have to plug in, the easier it is for us anyway. Okay, so now, if we take our derivative, we will get secant squared theta times d theta dt equals, and hopefully you remember this one, h over 200 is really 1 over 200 times h, so h, the derivative is dh dt. Now this is a very, very tricky part of this problem. Before I start writing any parentheses, just notice what information we have. We already have dh dt, 10 meters per second, to fill in right there. The 150 meters goes nowhere, and we're somehow supposed to solve for d theta dt. So this is the issue. If you're trying to figure out what do we plug in for theta, it might take quite a long time in order to get all that information out. So the better way of thinking of this is by doing the following. I'm going to ask us to figure out what secant squared theta is all at once. Okay? Now we're going to solve for d theta dt. d theta dt, so we're just going to leave that there. And this is going to be equal to 1 over 200 and then times dh dt, which we know to be 10. Now, right here, how do you figure out what secant squared theta is? Well, remember when they told us that the height of the balloon was 150 meters? If you think about this situation here, we've done something similar to this before. Even though the problem is changing and in constant movement, there is a moment that we could freeze time. And we know that the camera 200 meters away is measuring the balloon, which is 150 meters into the sky. Now, if this here is theta, and if I asked you, can you figure out what secant of theta is? Well, hopefully you'll think this through and realize that secant of theta is simply the reciprocal of cosine. And if you're looking at this picture here, how would you figure out what cosine of theta is? Well, cosine is based on SOHCAHTOA. It's the adjacent side right here over the hypotenuse, which is there. Now, you've dealt with this situation before. If you know that this side is 150 and you know that this side here is 200, could you calculate the length of that hypotenuse? Well, using Pythagorean Theorem, we could easily do that. So, if you go with 15 squared plus, if you go with 150 squared plus 200 squared equals x squared, you could solve for that x variable. But I will tell you, 150, 200, and 250 is a multiple of 15, 20, 25, which is a multiple of 3, 4, 5. This is just a really long, complicated way of me explaining. I don't want to do all the work because I know that that length is going to be at 250. You can do Pythagorean Theorem as much as you'd like on that question. So, if cosine is the adjacent over the hypotenuse, then what is secant? Choshakao. It would be the hypotenuse over the adjacent. It's simply cosine upside down. So, secant of theta would be 250 over 200, right? Which we could easily simplify if you divide not just by 10 here, but if you actually divide by 50, you'll get 5 over 4. So this problem takes a pretty interesting turn. However, if you're trying to solve for secant squared theta, my suggestion is don't solve for theta. Instead, analyze the situation at hand, and you can figure out what secant of theta actually equals. So since it's 5/4, let me actually square it to get 25 over 16. All right. Now finally, in order to solve for theta here, let's go ahead and simplify this. So on the right side, we already had 10 over 200, which we could simplify, but we're going to multiply both sides by 16 over 25. And because this problem is a calculator active question, I don't really feel like multiplying all that out by hand. So 160 divided by 200 times 25, this will give you 0.32, and this is going to be radians per minute, I believe. Radians per second, sorry about that. So, there is our answer to this question right here. And that concludes the final video of 4.6 related rates. Go to sleep.